Somewhere beyond the reach of the sun, a small machine is drifting through the dark, carrying a golden record, a fading heartbeat of electricity, and 47 years of quiet momentum. Welcome to the Sleepy Lab. Tonight, we follow Voyager 1 from its launch pad to the very edge of the solar system and into the space between the stars. If you find comfort here, consider subscribing, one sleepy soul at a time. Now, let's begin. On September 5th, 1977, a rocket lifted from Cape Canaveral, carrying a spacecraft no larger than a small car. The rocket was a Titan III, a tall, deliberate machine that had carried other probes into the deep before. But this time, the payload was different. This time, the destination was not a planet, or a moon, or even the edge of the solar system, as anyone then understood it. This time, the destination was simply outward. The spacecraft was called Voyager 1, and the mission, as originally planned, was modest. 4 years. Jupiter, then Saturn. A brief look at two of the solar system's giants, and then silence. That was the plan. But the universe had other ideas. To reach Jupiter, Voyager 1 did not travel in a straight line. Nothing in space ever does. It curved through the inner solar system, gathering speed, following the invisible geometry of gravity. And when it arrived at Jupiter in the spring of 1979, it did not simply pass by. It fell toward the planet, let Jupiter's enormous gravity pull it close, and then swung outward again, faster than before, much faster. This maneuver, a gravitational slingshot, added enough velocity to carry Voyager 1 not just to Saturn, but beyond, far beyond anything the original mission had imagined. Jupiter gave the spacecraft a gift it would carry for the rest of its existence. But before it left Jupiter behind, Voyager 1 looked down. Among the moons orbiting that vast planet, one in particular held something no one had expected to find. The moon was called Io, a small, dense world caught in a constant gravitational tug-of-war between Jupiter and its neighboring moons. That tidal squeezing generates enormous heat deep inside Io's interior. And that heat has to go somewhere. Voyager 1's cameras captured what that heat does. Active volcanoes. Eruptions rising hundreds of kilometers above the surface, plumes of sulfur arcing slowly against the black sky. It was the first time volcanic activity had ever been observed on a world other than Earth. Io was alive in a way no one had predicted. Quietly, violently, perpetually alive. Voyager 1 also turned its instruments toward Jupiter itself, toward the Great Red Spot, that ancient oval of rust and amber that had been observed from Earth for centuries. From a distance, it had always looked like a simple blemish on the planet's face. Up close, it was something else entirely. The Great Red Spot is a storm, but not a storm in any simple sense. It is a layered system of winds rotating within winds, each band moving at a different speed, in a different direction, interacting with the others in patterns that have persisted for hundreds of years, perhaps longer. The storm is older than most of the nations on Earth. It turns slowly, endlessly, with a kind of patience that has no human equivalent. From Jupiter, Voyager 1 continued outward, carried now by the speed Jupiter had given it, moving through the cold middle distance of the solar system. Saturn waited ahead, a planet so visually distinct from everything else in the sky that even ancient observers knew it was different. Voyager 1 arrived at Saturn in November of 1980. And the rings? From Earth, Saturn's rings look like a single flat disk, smooth and luminous. Voyager 1 revealed what that disk is actually made of. Not a solid surface, not a sheet of ice, but countless individual particles, each one orbiting Saturn on its own path, each one separate from all the others. Some of those particles are no larger than a grain of dust. Others are as large as a house, tumbling slowly in the dark, made of ice that has been frozen for billions of years. There are so many of them, moving in such precise formation that from a distance they appear solid. But they are not. They are a crowd, an immense, silent crowd of ice, each piece keeping its own quiet orbit around a planet it will never touch. The rings were not the only revelation at Saturn. Voyager 1 passed close to a moon called Titan, the largest of Saturn's mini-moons, and one of the most unusual objects in the solar system. Titan is wrapped in a thick atmosphere, mostly nitrogen, hazy and orange, opaque enough that Voyager's cameras could not see the surface beneath it. But the instruments could measure what the cameras could not see. The atmospheric pressure at Titan's surface is higher than the pressure at sea level on Earth. A dense, cold, chemically complex envelope of gas surrounding a world that, in some ways, resembles a frozen early Earth. The flyby of Titan was scientifically essential, but it came with a consequence. To pass close enough to Titan to gather that data, Voyager 1 had to follow a trajectory that bent it sharply out of the flat plane of the solar system, the ecliptic plane, where most of the planets orbit. That bend was permanent. After Titan, Voyager 1 could never reach Uranus or Neptune. The geometry of the encounter had decided its future. And its future was not more planets. Its future was the open dark. After Saturn, there were no more targets, no more scheduled flybys, no more planned encounters. The original mission was, technically, complete, but the spacecraft kept going. Of course it did. There was nothing to stop it. In space, an object in motion continues in motion, and Voyager 1 had been given more motion than almost any object humanity had ever launched. It was now on a trajectory that would carry it out of the solar system entirely, the first spacecraft ever aimed, however unintentionally at first, at interstellar space, at the space between the stars, at the vast, cold, ancient medium that fills the galaxy between one sun and the next. No one had ever sent anything there before. No instrument had ever measured it directly. Voyager 1 was going to change that, though it would take decades more to arrive. For now, in those early years after Saturn, the spacecraft simply traveled 17 kilometers every second through a solar system that was growing quieter and emptier with every passing year. The sun, which had been a blazing presence in the sky above Earth, was shrinking behind it. The planets were falling away one by one into the distance. And ahead, nothing visible, nothing mapped, nothing known with certainty. Just the slow, patient outward drift of a machine that had already seen more than it was ever designed to see, carrying its instruments, its fading power, and somewhere on its side, a golden record pressed with the sounds of a world it would never return to. The journey was only beginning. There was a moon at Saturn that no one fully understood. Titan, the largest of Saturn's moons, had long been a mystery. It was known to have some kind of atmosphere, but the nature of that atmosphere, its depth, its composition, its pressure, these things were uncertain until Voyager 1 arrived. What the spacecraft found was not what most scientists had expected. Titan's atmosphere was thick, genuinely, substantially thick, a dense envelope of nitrogen, layered and opaque, pressing down on the surface with a pressure greater than the air at sea level on Earth. Not slightly greater, meaningfully greater. About 1.5 times what a human being would feel standing on the ground here. The surface itself remained hidden beneath orange haze. Voyager's cameras could not see through it, but the instruments could measure what surrounded the moon, and what they measured was remarkable. A world wrapped in chemistry, in nitrogen and organic compounds, in a kind of cold, slow atmospheric complexity that hinted at processes no one had anticipated finding so far from the sun. That flyby changed everything about Voyager 1's path. To get close enough to Titan to study it properly, the spacecraft had to follow a trajectory that bent it, sharply, irrevocably, out of the flat plane in which the planets orbit, the ecliptic plane, the broad, thin disk of the solar system where Earth and Mars and Jupiter and Saturn all trace their slow circles around the sun. Once Voyager 1 swung past Titan, It was no longer traveling within that plane. It was angled upward, out of it, climbing away from the solar system's disk at an angle that made any further planetary encounters impossible. Uranus was out there. Neptune was out there. But they were in the plane, and Voyager 1 was leaving the plane behind. That was the trade. Titan, in exchange for everything else. And so the spacecraft continued outward, not toward another planet, not toward any mapped destination, but simply outward, into the increasing emptiness beyond Saturn, into the long, dark, uncrowded space that lies between the outer solar system and whatever comes after it. It carried its instruments. It carried its fading warmth from 3 small generators quietly converting the decay of plutonium into electricity. And it carried something else, something that had nothing to do with science. Exactly, and everything to do with the kind of creatures who had built it. On Voyager 1's side, bolted to the spacecraft, there is a record. A physical record, a 12-inch gold-plated copper disc, sealed in an aluminum cover, with a cartridge and needle included, so that whoever finds it might have some chance of playing it. The cover is engraved with instructions, diagrams, a kind of visual key, drawn in the language of physics and mathematics, which are the only languages that might survive the crossing of interstellar space and still be understood on the other side. The record contains sounds from Earth, the sound of wind, of rain, of surf against the shore, of a mother speaking softly to a newborn child, of footsteps, of a heartbeat, of thunder rolling across a plain. It contains music, pieces chosen from across human cultures and across centuries of time. A Javanese gamelan, a Navajo night chant, a Bach prelude, a Georgian chorus, a Peruvian wedding song, a piece of Chuck Berry that almost didn't make it onto the final selection. It contains greetings in 55 languages, some of them ancient, some of them spoken by only a small number of people on Earth at the time of recording. Each greeting is brief. Each one says, in its own way, something like, "We are here, and we wanted you to know." It contains encoded images, photographs that can be reconstructed from the signal on the disk if the finder knows how to look. Images of humans, of animals, of landscapes, of a woman in a supermarket, of a child eating an ice cream cone, of the sun rising over a horizon. The record was assembled by a small committee over several months in 1977. The astronomer Carl Sagan led the effort, along with a group of colleagues who understood that they were not making a scientific document. Exactly, they were making something closer to a portrait of a species compressed onto a disk, sent outward into a silence so vast that the odds of it ever being found are, by any honest calculation, extraordinarily small. And yet, it was made with care, with genuine care. The people who chose those sounds and those images understood that they were probably making something no one would ever hear. They did it anyway. There is something in that, something quiet and serious and worth sitting with for a moment, in the idea of sending a message you have almost no reason to believe will ever arrive. Voyager 1 carried that record outward through the 1980s, past the orbit of Uranus, which it never visited, past the orbit of Neptune, which it also never visited, growing farther from the sun with every passing year, every passing month, every passing day. By 1990, it had traveled far enough that someone at NASA had an idea. The spacecraft still had its cameras. They were still functional. And from where Voyager 1 now sat, more than 6 billion kilometers from the sun, it was possible, just barely possible, to turn those cameras back toward the inner solar system and take one last look. The result was a mosaic of 60 frames, a family portrait of the solar system, taken from the outside, looking in. Most of the planets appeared as faint points of light, barely distinguishable from the background. Some were almost invisible. And Earth, the world that had built this spacecraft, that had pressed those sounds onto that golden record, that had tracked this machine across 13 years of empty space. Earth appeared as a pale blue dot, less than a single pixel wide, suspended in a beam of scattered sunlight that crossed the frame like a shaft of dust in a darkened room. The dot was so small, so faint, so easily overlooked that it required careful examination to find it at all. And yet, everything that had ever happened in human history had happened on that dot. Every person who had ever lived, every city ever built, every war ever fought, every piece of music that had been chosen for that golden record. All of it contained in something smaller than a grain of sand in a photograph. Carl Sagan wrote about that image later. He wrote about the smallness of it and about what that smallness meant, not as a cause for despair, but as a reason for something like humility, for a gentler way of treating one another and the world we share. His words have been read many times since then, in many places, by many people lying in the dark. Perhaps some of them were lying in the dark the way you are now. Voyager 1 took that photograph, and then its cameras were turned off for the last time. There was no longer enough power to spare for imaging. The spacecraft had other work to do. Instruments still listening, still measuring, still sending back data across a distance that was growing longer every single day. It continued outward. 17 kilometers every second, quietly, without ceremony, carrying its record and its instruments, and the faint, patient signal of its transmitter into the space beyond the solar system's edge. The sun was now just the brightest star in its sky, and ahead, the interstellar medium, the ancient, thin, cold material that fills the space between one star and the next. A place no instrument had ever sampled. A place that, for all of human history until very recently, had existed only in theory. Voyager 1 was still decades away from reaching it, but it was going. That pale blue dot in the 1990 photograph, less than a single pixel wide, suspended in a narrow beam of scattered sunlight, like a mote of dust caught in a shaft of light through a window. That was everything. Every person who had ever lived, every city, every ocean, every mountain range, every moment of recorded history contained in something too small to see clearly. And Voyager 1 was already leaving it behind. It had been traveling for 13 years by then, and it would travel for many more, through a region of space that most people never think about, and that scientists, until recently, could only describe in broad strokes. To understand where Voyager was going, it helps to understand what surrounds us. The sun does not simply sit still and shine. It breathes, in a way, constantly, in every direction. It releases a stream of charged particles, mostly protons and electrons, moving outward at somewhere between 400 and 800 kilometers per second. This is the solar wind. It does not stop at the planets. It does not stop at the orbit of Neptune, the outermost of the 8 planets, which lies roughly 30 astronomical units from the sun. It keeps going, far beyond. 1 astronomical unit is the distance from Earth to the sun, about 150 million kilometers. Neptune sits 30 of those units out, but the solar wind reaches much, much farther than that. As it flows outward, the solar wind carries with it the sun's magnetic field, stretched and shaped by the wind itself into a vast, enveloping structure. This structure, the region of space where the sun's wind and magnetic field dominate, is called the Heliosphere. It is enormous. The Heliosphere extends perhaps 100 astronomical units from the sun in some directions, and farther in others. It is the sun's domain, the bubble of influence that our star has carved out for itself in the surrounding interstellar space. Everything within it, every planet, every moon, every comet and asteroid and drifting grain of dust, exists inside this bubble. And it is not a perfect sphere. The solar system is moving through the galaxy, not standing still, but traveling, the sun and all its planets sweeping through space at a considerable speed in the direction of the constellation Hercules. As the heliosphere moves through the interstellar medium, it is compressed on the leading side, the side facing the direction of travel, and stretched out behind like the wake of a slow ship. The shape is elongated, asymmetric, more like a comet than a ball. The side pressing into the interstellar wind is pushed inward. The trailing side extends further back into the darkness. This is the shape of the sun's reach, not round, but worn and sculpted by its passage through the galaxy. Voyager 1 was moving through this structure outward, always outward, and eventually it would reach the edge of it. But the edge is not a single line. The first boundary Voyager would encounter, the first sign that the solar wind was losing its grip, is called the termination shock. Here is what happens there. The solar wind, flowing outward for billions of kilometers, eventually meets resistance. The interstellar medium pushes back, and at a certain distance, the solar wind can no longer maintain its speed. It slows, abruptly, dramatically, from supersonic to subsonic, the way a fast-moving stream of water suddenly spreads and slows when it hits a flat surface. The energy doesn't disappear, it gets converted. The plasma heats up, compresses, becomes turbulent, but the outward rush, that clean, supersonic flow from the sun, comes to an end. This is the termination shock. Scientists had predicted it would exist. They had modeled it, debated its location, estimated its distance. But no instrument had ever measured it directly. No spacecraft had ever crossed it. Until Voyager 1. In approximately 2004, 27 years after launch, Voyager 1 crossed the termination shock. It was at a distance of roughly 94 astronomical units from the Sun, 94 times the distance from Earth to the Sun, about 14 billion kilometers. The instruments registered the change. The solar wind slowed. The plasma density shifted. The magnetic field fluctuated in ways consistent with what the models had predicted, though not perfectly consistent. As it turned out, the data was more complex than expected. The termination shock was not a clean, stable boundary. It moved. It rippled. Voyager may have crossed it more than once as the boundary oscillated back and forth around the spacecraft. The solar system's edge was not a wall. It was more like a shoreline, shifting with the tides. And beyond it lay something new. Beyond the termination shock, the solar wind still existed, but it was no longer the same wind that had left the sun. It was slowed, compressed, heated, and confused, no longer flowing cleanly outward, but tumbling and churning in a thick region of disturbed plasma. Voyager 1 had entered this region, and it would spend years crossing it. But that is a story for a little later. For now, just hold the image of it. A small machine, built by human hands in the 1970s, crossing a boundary that no instrument had ever reached. 94 times the distance from Earth to the Sun, moving at 17 kilometers every second, and still going. The Sun, behind it, was a point of light. Bright, still the brightest thing in its sky, but a point. Nonetheless, the pale blue dot was somewhere near that point, invisible at this distance, smaller than any instrument could resolve. And ahead, the heliosphere continued for a while longer, more turbulence, more complexity, more boundaries yet to cross. Voyager 1 was patient. It had no choice but to be. It simply moved, as it had always moved, through the dark and the cold and the silence, carrying its instruments and its record and its faint signal home. 17 kilometers every second. Every second of every minute, of every hour, of every day, for decades. Quietly. To understand where Voyager 1 was and what it was crossing, it helps to hold a sense of the distances involved. One astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers, a distance so large that light itself, traveling at roughly 300,000 kilometers every second, takes about 8 minutes to cover it. 8 minutes. When you look at the Sun, you are seeing it as it was 8 minutes ago. That is how far away it is. And Voyager 1, at the moment it crossed the termination shock, was 94 of those units from home. 94 times 150 million kilometers, a number that doesn't resolve easily into feeling, only into quiet awe. And it had only just reached the beginning of the next region. Beyond the termination shock, the solar wind does not simply stop. It enters a different state, a thick, disordered region called the Heliosphere. Here, the plasma that was once streaming outward at hundreds of kilometers per second has been slowed, compressed, and heated. It presses against something it cannot yet pass through, and so it accumulates. It churns. The Heliosphere is not thin. Estimates place its thickness somewhere between 25 and 50 astronomical units, which means, in the most grounded terms available, somewhere between roughly 4 billion and 7.5 billion kilometers of disturbed, turbulent plasma, a region wider than the entire span from the Sun to Neptune, perhaps wider still. Voyager 1 spent about 8 years crossing it. 8 years of instruments recording, of signals traveling home, of engineers on Earth reading data from a machine moving through a place no machine had ever been. 8 years of the Heliosphere. And what the Heliosphere gave back was not what anyone had quite expected. Before Voyager reached this region, the models were reasonable, considered, built from the best physics available. Scientists expected the Heliosphere to be relatively uniform, a thick but predictable layer, compressed and warm, with the solar wind spreading outward in a broadly consistent way. Disordered, yes, but in a way that could be anticipated and described. What Voyager found was something else. The solar wind inside the Heliosphere does not flow in a single direction. It no longer moves cleanly outward, away from the Sun, as it had for the entire journey before. Instead, it becomes irregular. It folds back on itself in places. It shifts. The plasma moves in ways that the instruments could detect, but that the models had not predicted with any precision. The data came back slowly, over months and years, and the picture it assembled was one of genuine complexity. Layers of variation. Regions where the magnetic field behaved unexpectedly. Places where the particle counts rose and fell in patterns that didn't match the smooth, gradual transition the models had described. The Heliosphere was not a quiet waiting room between the solar wind and interstellar space. It was its own environment, dense, pressured, and strange. There is something worth sitting with in that. The scientists who built Voyager, who designed its instruments, who had spent careers thinking carefully about what this region might be like, they were surprised. Not wrong in their foundations, but surprised in the details. The universe, as it so often does, turned out to be more intricate than the models. And Voyager moved through all of it. Steadily, without adjustment, without complaint, 17 kilometers every second, through 8 years of turbulence it could not feel and could only measure. Somewhere in those 8 years, the Sun had grown even fainter behind it. Still the dominant source of light in Voyager's sky, but diminished. A bright star among stars, rather than the overwhelming presence it had been at the beginning of the journey. And ahead, something was waiting. A boundary, the outermost boundary of everything the Sun has ever touched. It is called the Heliopause. The Heliopause is the place where the Sun's influence ends, not gradually, not in a slow fade, but at a specific threshold. It is the boundary where the outward pressure of the solar wind, even in its slowed and turbulent Heliosphere state, exactly balances the inward pressure of the interstellar medium, the material between the stars, pressing in from all directions, from the vast dark between one sun and the next. At the Heliopause, those two pressures meet and hold each other. Neither wins. The solar wind cannot push any further outward. The interstellar medium cannot press any further inward. And so a boundary forms, not a wall, not a surface you could touch, but a region where the balance is struck and held. On one side of that boundary, everything is still. In some sense, the Sun's. On the other side, it is not. For 8 years, Voyager 1 moved through the Heliosphere toward that boundary, its instruments measuring, its transmitters sending, its golden record riding along in silence. The plasma around it was compressed and heated and irregular, but it was still solar plasma, still particles that had once left the Sun, that carried the sun's magnetic signature, that were part of the vast bubble the sun had blown into the galaxy over billions of years. And then, in August of 2012, 35 years after launch, Voyager 1 reached the Heliopause. At a distance of about 121 astronomical units from the sun, 121 times 150 million kilometers. A number that settles into the mind not as a measurement, but as a kind of silence. The crossing was not announced by a single instrument reading. It was confirmed gradually through a combination of data, plasma waves, magnetic field readings, particle counts, each one telling part of the same story. The density of the surrounding plasma increased sharply. The character of the magnetic field shifted. The particles that had come from the sun grew sparse, and the particles that had come from elsewhere in the galaxy grew more numerous. Voyager 1 had crossed the Heliopause. It had left the sun's domain. For the first time in the history of human exploration, a machine built on Earth was traveling through interstellar space, the space between the stars, the space that had existed long before the sun was born and will exist long after it is gone. The signal carrying that news traveled home at the speed of light, and even at that speed, it took hours to arrive. That signal, faint beyond almost any ordinary measure, crossed 121 astronomical units of space to reach the antennas waiting for it on Earth, and the people who received it had spent years, in some cases decades, waiting for exactly this moment. The Helios was behind Voyager now. All that turbulence, all that compressed and churning plasma, all those years of crossing a region more complex than anyone had fully anticipated, behind it. Ahead was something quieter, something older. The interstellar medium, the thin, cold, ancient material that fills the space between one star and the next. Hydrogen and helium, mostly with traces of heavier things, spread so thinly that a volume the size of a room might contain only a handful of atoms. And Voyager 1 was moving through it, 17 kilometers every second, into the dark between the stars. The crossing itself was not announced by a single moment. There was no single instrument that flickered and said, "Here, this is the place." It was quieter than that, and more certain for being quiet. The plasma wave instrument noticed something first: oscillations in the surrounding medium, a kind of ringing in the charged gas that Voyager was moving through. Those oscillations had a frequency, and from that frequency, scientists could calculate a density, and the density had changed. It had not changed gradually. It had changed sharply. The plasma surrounding Voyager 1 in August of 2012 was roughly 40 times denser than what the spacecraft had been measuring in the Heliosphere. 40 times. Not a drift, not a gradual thickening, a distinct step, like crossing from shallow water into deep. That sharp increase in plasma density was one of the clearest signatures scientists had been waiting for. It meant the solar wind's thin, outward-flowing material had been left behind. What surrounded Voyager now was something else entirely. But the plasma wave data alone was not enough to confirm the crossing. Science, at its most careful, asks for more than one voice. The magnetometer was also listening. It had been measuring the direction and strength of the magnetic field threading through the space around Voyager for decades, and as the spacecraft moved through the heliopause, the field shifted. Not dramatically. The rotation was smaller than many models had predicted, but measurably, clearly, in a direction consistent with the interstellar medium's own magnetic orientation rather than the sun's. The field that had accompanied Voyager across 35 years and 121 astronomical units of space was giving way to a different field, one that belonged to the galaxy, not to the sun. And then there were the particles. Voyager's cosmic ray detectors had been watching two populations of particles for years. One population originated from the sun, lower energy particles carried outward by the solar wind. The other came from far beyond, galactic cosmic rays, high-energy particles born in the violence of distant supernovae, traveling across the galaxy for millions of years before arriving at the edge of our solar system. As Voyager approached the Heliopause, the solar particles began to thin, and the galactic particles began to rise. The two curves crossed and then separated, and the message was clear. The sun's particles were behind. The galaxy's particles were all around. 3 instruments, 3 independent lines of evidence, all pointing to the same conclusion. Voyager 1 had crossed the Heliopause in August 2012, and the confirmation, built carefully from plasma and magnetism and particle counts, was as solid as anything the mission had ever produced. What it had entered was the interstellar medium. That phrase carries a weight that is easy to pass over too quickly. The interstellar medium is not empty space in the way we sometimes picture emptiness. It is material, real, physical material that fills the vast distances between one star system and the next. Gas and dust and charged particles spread across scales that have no comfortable human equivalent. It is the substance of the galaxy itself, the medium through which stars are born and through which their light travels, and through which, now, a small machine from Earth was quietly moving. Near our solar system, this medium is dominated by hydrogen, single atoms of it, mostly, drifting, unattached to anything. Alongside them, helium, the second simplest element, forged in the first minutes after the universe began. And then, in much smaller quantities, traces of heavier things, carbon, oxygen, traces of iron and silicon and other elements scattered by ancient stars that lived and died long before our sun existed. The interstellar medium is, in a sense, the accumulated exhaust of stellar history, the material left behind by generations of stars, slowly mixing, slowly cooling, slowly waiting to be gathered again into something new. It is extraordinarily thin. A cubic centimeter of the interstellar medium near the Heliopause contains, on average, less than 1 particle, sometimes far less. The volume of a large room, filled with this material, might hold only a few thousand atoms in total. By any earthly standard, it is as close to nothing as matter can be, while still being something. And yet, it has a temperature. This is one of those facts that requires a moment to sit with. The interstellar medium near the Heliopause is estimated to be somewhere between 30,000 and 50,000 Kelvin. That is hotter than the surface of the sun. Hotter, by a wide margin, than almost anything a person encounters in ordinary life. And yet, it would not feel hot. Temperature in a gas is a measure of how fast individual particles are moving. In the interstellar medium, the particles that are present move very quickly indeed, hence the high temperature. But there are so few of them, so vanishingly few, that the total energy they carry is almost nothing. A thermometer placed in the interstellar medium would not register warmth, because warmth requires particles to collide with the thermometer and transfer their energy. And in a medium this sparse, those collisions almost never happen. The heat is real, and it is also, in any practical sense, absent. It is a cold that contains fire, spread too thin to burn. Voyager 1 moved through all of this without ceremony, 17 kilometers every second, the same speed it had been traveling for years. There was no jolt, no resistance, no moment of passage that the spacecraft itself could have registered. The Heliopause is a boundary defined by pressure, the point where the sun's outward push and the interstellar medium's inward push arrive at equilibrium. And crossing it left no physical mark on the spacecraft. Only the instruments knew. Only the data knew. And the data was still traveling home. Every measurement Voyager made in those weeks and months around the crossing had to travel back across 121 astronomical units of space. At the speed of light, that journey takes over 16 hours one way. The scientists waiting on Earth were not watching in real time. They were reading a record of something that had already happened, transmitted across a distance that makes the word distance feel inadequate. The signal itself was almost nothing by the time it arrived. A whisper of radio energy, carrying the news of a historic crossing, arriving at the large dish antennas of the Deep Space Network with a power so small it would take trillions of such signals, arriving simultaneously to light a single small bulb, and yet the antennas heard it, and the engineers decoded it, and the scientists read what Voyager had found. Plasma denser than expected. A magnetic field shifted toward the galaxy's own orientation. Cosmic rays rising. Solar particles falling. A boundary crossed. The interstellar medium entered. For the first time in the history of the species that built it, a human-made object was sampling the material between the stars, the ancient, thin, cold, and hot, nearly empty substance that fills the space between one sun and the next. Hydrogen and helium and traces of everything that stars have ever made, drifting in the dark between the fires. And Voyager 1 was moving through it, quietly, without ceremony. 17 kilometers every second, in the direction of the constellation Ophiuchus, carrying its golden record, carrying its fading power, carrying 47 years of accumulated distance from the world that made it. Still listening. Still sending. The interstellar medium is, in a technical sense, extraordinarily hot. Temperatures near the Heliopause run somewhere between 30,000 and 50,000 Kelvin, hotter than the surface of many stars. And yet, if you were somehow suspended in that space, you would not feel warmth. You would feel nothing at all. Because temperature, in the way we experience it, is not just a number, it is a measure of how fast particles are moving. And in the interstellar medium, the particles move very fast indeed, but there are almost none of them. A cubic centimeter of that space might hold fewer particles than the most perfect vacuum ever created in a laboratory on Earth. Heat requires contact. It requires something to touch you, to transfer its motion to yours. And out there, beyond the Heliopause, the particles are so sparse, so far apart from one another, that the warmth they carry has almost nowhere to go. So the interstellar medium is simultaneously hot and, in every practical sense, cold. A quiet paradox, drifting in the dark between the stars. Voyager 1 moved through it, and it listened. One of the instruments still functioning aboard the spacecraft is called the Plasma Wave Science Subsystem. It does not measure particles directly the way a net might catch fish. Instead, it listens for oscillations, tiny, rhythmic disturbances in the plasma, waves that ripple through the charged gas the way sound waves ripple through air. When a plasma is disturbed by the spacecraft's own passage or by events far away, it rings at a frequency that depends on how many particles are present. The denser the plasma, the higher the frequency of those oscillations. And so, by listening carefully to the pitch of those waves, scientists could calculate the density of the medium Voyager was moving through. What they found was striking in a quiet way. The plasma in the interstellar medium, the material just beyond the Heliopause, was roughly 40 times denser than the solar wind plasma Voyager had been traveling through in the Heliosphere. 40 times. Not a gradual fade, not a slow thinning of one medium into another. A sharp, meaningful difference, measured in the oscillations of a plasma wave instrument aboard a spacecraft, the size of a small car, drifting alone in the space between the stars. The Heliosphere, it turned out, had been holding something back. Not just the solar wind, not just the sun's magnetic field, but the interstellar medium itself, pressing inward from all directions, held at bay by the outward pressure of everything. The sun continuously exhales. And beyond that boundary, the galaxy's own material waited, denser and older and indifferent. Voyager was now inside it. There is something else the Heliosphere holds back, though it does so imperfectly, and the story of that shielding is written in the data Voyager's cosmic ray detectors returned. Cosmic rays are not rays in the way. Light is a ray. They are particles, protons, atomic nuclei, electrons, accelerated to enormous energies by some of the most violent events in the galaxy. Supernovae, the deaths of massive stars, flinging matter outward at a fraction of the speed of light. Distant pulsars, spinning hundreds of times per second, their magnetic fields acting as vast natural accelerators. The regions around black holes, where matter falls inward and energy pours outward. These particles travel across the galaxy for thousands or millions of years before arriving at the edge of our solar system. And the heliosphere deflects many of them. Not all. The most energetic cosmic rays pass through as though the heliosphere were barely there. But a meaningful fraction, the lower energy galactic cosmic rays, are scattered and slowed and turned aside by the sun's magnetic field and the turbulent plasma of the heliosheath. The result is that the inner solar system, where Earth orbits, sits inside a kind of partial shelter. Not a perfect one, but a shelter nonetheless. As Voyager 1 traveled outward through the heliosheath, its cosmic ray detectors watched this shelter from the inside. And as the spacecraft approached the Heliopause, something began to change. The count of galactic cosmic rays, particles arriving from the wider galaxy, began to rise. Slowly at first, then more steeply. The closer Voyager came to the boundary, the thinner the shielding above it, the more of the galaxy's high-energy particles were able to reach the spacecraft's detectors. And then, as Voyager crossed the Heliopause in August of 2012, the count rose sharply. A clear signal, unmistakable in the data. The spacecraft had passed beyond the shelter. It was now exposed to the full flux of galactic cosmic rays, the unfiltered particle environment of interstellar space, the same environment that exists between every star in the galaxy, the same ancient rain of high-energy particles that has been falling through this region of space since long before the sun was born. At the same moment, something else happened in the data. The lower energy particles, the ones originating from the sun, carried outward by the solar wind, filling the heliosphere with the sun's own particle signature, those particles dropped. Sharply, as though a door had closed. On one side of the Heliopause, the sun's particles. On the other side, the galaxy's particles. And Voyager's instruments, crossing that boundary, recorded both transitions simultaneously, the solar flux falling, the cosmic ray flux rising, in the same window of data, at the same distance from the sun. It was, in its way, a portrait of a boundary. Not a wall, not a hard edge you could touch, but a place where two vast, slow-moving systems press against each other and hold their ground, where the sun's reach ends and the galaxy's presence begins. Scientists had expected something like this. The broad shape of it had been predicted for decades, but the details were more complex than the models had suggested. The boundary was not perfectly sharp. There were fluctuations, layers, hints of structure within the transition. The magnetic field had shifted, but not by as much as expected. The plasma density had jumped, but the jump had its own texture. The heliosphere's edge, it turned out, was not a clean line drawn across space. It was more like a shoreline, dynamic, layered, moving slightly with the sun's own breathing, shaped by the pressure of the interstellar wind flowing past from the direction of the solar system's motion through the galaxy. A shoreline that no instrument had ever sampled from the outside. Until Voyager. And now the spacecraft moved beyond it, carrying its instruments, carrying its fading warmth, carrying the golden record with its sounds of a living world. Ocean waves, wind, the low rumble of thunder, music made by human hands, all of it drifting outward into a medium that is simultaneously ancient and thin and vast beyond easy reckoning. 17 kilometers every second. The signal traveling back toward Earth at the speed of light, taking more than 22 hours to complete the journey. 22 hours. A radio wave, moving at 300,000 kilometers per second, needing nearly a full day just to cross the distance between Voyager and the planet that built it. And still, the antennas listen. And still, the data comes. The magnetic field changed too. Not dramatically, not all at once, but measurably, in the way that instruments record a quiet shift in the character of the space around them. The field that had accompanied Voyager for 35 years, the Sun's own field, stretched and wound outward across billions of kilometers. That field began to give way to something older, something that did not originate with our star. The interstellar medium carries its own magnetic field, a field woven by the slow drift of charged particles between the stars, shaped over timescales that dwarf the age of the solar system itself. And as Voyager crossed the Heliopause, its magnetometer registered the transition, a rotation in the field's orientation, a subtle but real change in the direction the field lines were pointing. Scientists had expected this. They had built models, run the calculations, predicted that the rotation would be significant, that the Sun's field and the interstellar field would meet at a steep angle, and that crossing from one to the other would register as a clear, dramatic turn in the data. What Voyager found was quieter than that. The rotation was real, but smaller than most models had anticipated. The two fields, it seemed, were not as misaligned as expected, or perhaps the boundary region itself had smoothed the transition in ways the models had not fully captured. This is one of the things that makes Voyager's data so valuable and so humbling. Not because it confirmed what we thought we knew, but because it didn't, not entirely. The universe, as it tends to do, turned out to be more nuanced than the equations. And the boundary itself. The heliopause is not a wall standing fixed in space. It breathes. The Sun breathes, and the heliopause moves with it. Every 11 years or so, the Sun passes through a cycle of activity, periods of greater intensity, when solar flares and coronal mass ejections send more material streaming outward, when the solar wind carries more pressure, more energy, more force. During those periods of high activity, the heliosphere swells slightly, pushing the heliopause a little farther out into the interstellar medium. And then the Sun quiets. Solar minimum arrives, the wind eases, and the boundary drifts inward again, contracting like a slow tide pulling back from a shore. Voyager crossed that boundary at a particular moment in the Sun's cycle, a snapshot of a moving line. The heliopause that Voyager sampled in August of 2012 was not the heliopause of a decade earlier, and not the heliopause of a decade later. It was the boundary, as it existed on those specific days, at that specific location, shaped by the particular balance of pressures present at that moment in time. There is something quietly remarkable in that. A spacecraft traveling for 35 years, crossing a boundary that itself is always in motion, and the crossing still happened. The data still came through, the instruments still recorded what they found. What they found was layered. Voyager's data suggested that the heliopause is not a single clean surface, not one line where the solar wind ends and the interstellar medium begins. There appear to be sub-boundaries, regions within the transition zone, where the properties of the plasma shift in steps rather than all at once. A structure more like a series of nested membranes than a single skin, each layer marking a different balance of pressures, a different mixture of particles, a different configuration of the magnetic field. The models had imagined something simpler, a cleaner edge, but the data kept returning with more texture, more complexity, more evidence that the boundary between our solar system and the rest of the galaxy is a place of ongoing negotiation rather than a fixed agreement. And just beyond that boundary, just outside the heliopause, in the interstellar medium itself, there is something else. A region that was not discovered by Voyager directly, but by light, ultraviolet light, observed by instruments looking outward from within the solar system. A place where interstellar hydrogen, flowing in from the surrounding galaxy, encounters the heliopause and slows, piles up, accumulates against the outer surface of the heliosphere the way water thickens just before a dam. This region is called the hydrogen wall. It is not visible in the ordinary sense. It does not glow in any wavelength that the eye could perceive, but it absorbs ultraviolet light in a particular way, and that absorption leaves a signature, a dimming. a spectral fingerprint that instruments can read. And through that reading, scientists inferred its presence. A wall of hydrogen, ancient and cold and patient, pressing gently against the outer edge of the bubble our sun has made. Voyager passed through the Heliopause and into the space just beyond it. Whether it passed through or near the hydrogen wall is a question that data does not answer with perfect clarity. The instruments were not designed with that specific boundary in mind, but the plasma wave readings, the particle counts, the magnetic field measurements, all of them together paint a picture of a region that is richer and stranger than the simple diagram of a sphere with a clean outer edge. The solar system, it turns out, does not end neatly. It fades. It negotiates. It leaves traces of itself in the surrounding medium, and the surrounding medium leaves traces of itself at the edge of the solar wind. The two regions interpenetrate slightly, influence each other, create transition zones that are neither fully one thing nor fully the other. This is what Voyager found at the edge. Not a wall, not a void, not a sudden silence, but a gradual, complex, layered transition into a medium that is ancient and thin and threaded with the magnetic memory of events that happened long before our sun was born. And Voyager moved through it, 17 kilometers every second, quietly, without ceremony, the way all truly long journeys proceed, not with a dramatic crossing, but with a slow accumulation of distance, 1 second at a time, one measurement at a time, the instruments still running, the transmitter still sending, the signal still making its way back across the widening gulf between the spacecraft and the world that launched it. More than 22 hours now for that signal to arrive. A radio wave traveling at the speed of light, crossing a distance so large that the number of kilometers requires 12 digits to write. And at the end of that journey, the signal arrives with almost nothing left of it, a whisper of energy, a few femtowatts, less power than a single cell of living tissue produces in a heartbeat, and yet the antennas find it. The Deep Space Network, with its great dishes turned toward the constellation Ophiuchus, catches that whisper and turns it back into data. Numbers, measurements, the quiet testimony of instruments operating at the edge of what is possible in a place no human-made object has ever been before. Every day, Voyager moves roughly 1.5 million kilometers farther from the sun, not rushing, not slowing, simply continuing as it has continued for nearly half a century, carrying everything it was given, its instruments, its fading warmth, its golden record with its ocean waves and its music and its encoded images of a small, living world, outward into the interstellar medium, into the local bubble, into the long dark between the stars. The data it returns grows older with each passing year, and still, scientists find new things in it. Still, papers are written, models are revised, understanding deepens. The edge of the solar system was not what we expected. It was more complex and more quiet than anyone had quite prepared for. The region Voyager now moves through has a name. The very local interstellar medium. It is the space immediately surrounding our solar system, the nearest neighborhood, in galactic terms. And even this nearest neighborhood is not empty. It is threaded with thin gas, with ancient dust, with the faint remnant fields of events that happened long before our sun was born. Our solar system is not sitting still within it. The sun, and everything bound to it, is moving through the galaxy at considerable speed. And the particular region we are passing through right now has its own character, its own history. It is called the local bubble. The local bubble is a large, low-density cavity in the interstellar medium, roughly 1,000 light-years across. By some estimates, it was carved out over millions of years by the shock waves of ancient supernovae, stars that burned through their fuel and collapsed and exploded, one after another, hollowing out this region of the galaxy the way a slow breath hollows out a space in fog. The gas here is thinner than the interstellar medium elsewhere. The dust is sparser. We live inside this cavity, and have for a very long time, though we only came to understand it relatively recently. Voyager is now moving through the inner edge of that cavity, through the very local portion of it, measuring it, in its quiet way, one day at a time. It travels at roughly 17 kilometers per second. Relative to the Sun, that is not slow, by any ordinary measure. 17 kilometers in a single second. In a minute, it covers more than 1,000 kilometers. In a day, it moves roughly 1.5 million kilometers farther from everything it came from. And yet, space is so large that this speed feels, in cosmic terms, like stillness. Expressed another way, Voyager covers about 3.5 astronomical units each year, 3.5 times the distance from the Earth to the Sun, in a year, and the nearest star system, a small, dim red dwarf called Proxima Centauri, lies roughly 268,000 astronomical units away. At Voyager's current speed, it would take approximately 73,000 years to cross that distance. 73,000 years. That is longer than modern human civilization has existed, longer than the oldest cave paintings, longer than the oldest known burial sites. It is a span of time that has no real anchor in human experience. It simply extends outward, the way the dark extends outward, without a visible end. And Voyager is not even headed toward Proxima Centauri. It is traveling in a different direction entirely, toward the constellation Ophiuchus. The 73,000 year figure is simply what the arithmetic produces when you divide the distance by the speed, a way of feeling the scale, not a destination. The actual closest approach Voyager will make to any star, as far as we can calculate, will happen in roughly 40, a star called Gliese 445, in the constellation Camelopardalis, a faint star, not visible to the unaided eye from Earth. Voyager will pass within about 1.6 light-years of it, still an enormous distance, still the deep cold of interstellar space. But the closest Voyager will come to another sun for as long as we can trace its path. No one will be there to observe it. There is no instrument aboard that will still be functioning. It will simply pass, in silence, at 17 kilometers per second, through the outer darkness near a star that has no name most people would recognize and continue onward. This is the nature of the journey now, not a mission in the operational sense, something quieter than that, a drift, a long, slow passage through a space that has no landmarks, no edges visible from within it, no way to feel the motion at all. And yet Voyager is not entirely alone in what sustains it. Even now, 3 small devices are still generating power aboard the spacecraft. They are called radioisotope thermoelectric generators. 3 of them, mounted on booms extending from the spacecraft's body. Each one contains a quantity of plutonium-238, a radioactive isotope that decays slowly and steadily, releasing heat as it does. That heat is converted into electricity through a process called the Seebeck effect, a quiet phenomenon in which a temperature difference across certain materials produces a small electrical current. No moving parts, no combustion, no fuel in the conventional sense. Just the slow, patient release of energy that was locked into the plutonium atoms long before the spacecraft was built. At launch, those 3 generators together produced about 470 watts of power, enough to run a few household light bulbs. Not much, even then, but enough, carefully managed, to operate the instruments and the transmitter and the systems that keep Voyager functioning. The plutonium decays at a known rate, and so the power declines at a known rate. By the mid-2020s, the output had fallen to roughly 240 watts, less than half of what it was at launch. Engineers have responded by shutting down instruments one by one, and heaters and systems that are no longer essential, preserving what remains for the instruments that still have something to say. The plasma wave subsystem, the magnetometer, the cosmic ray detectors, these still listen, still measure, still send their findings back across the distance, encoded in a radio signal so faint it arrives at Earth carrying only a few femtowatts of power. That signal travels at the speed of light, and it still takes over 22 hours to arrive. 22 hours at the speed of light. That is where Voyager is now, that far, that quiet, that alone in the dark between the stars. Moving at 17 kilometers per second through the very local interstellar medium, through the hollowed-out remnant of ancient stellar deaths, through a region of the galaxy our sun has been crossing for millions of years without our knowing. The power will not last much longer. A few more years, perhaps, depending on how carefully it is managed. And then the last instrument will go silent, and the signal will stop, and Voyager will become simply an object, a small, cold, human-made thing drifting through interstellar space with no voice left. But it will not stop moving. It will continue at 17 kilometers per second through the local bubble, past Gliese 445 in 40,000 years, through whatever lies beyond that, in the long dark that has no name we know yet. Carrying its golden record, carrying the sound of wind and rain and a mother's first words to her child, and music from a dozen human traditions, and the encoded image of a man and a woman standing against a blank background, small and hopeful and impossibly far from home. It will carry all of that outward indefinitely into a future so distant it cannot be imagined. And somewhere, right now, in the direction of Ophiuchus, it is moving. Quietly, without ceremony, 17 kilometers every second, into the dark. And yet the spacecraft is not silent yet. There is still a voice, still a thread of contact, stretched across a distance that has no easy comparison. To understand how that voice is possible, it helps to know what keeps Voyager 1 alive, what has kept it alive for nearly half a century, in a place where no sunlight reaches, where no battery could ever be recharged, where the cold of space is absolute and unforgiving. The answer is heat. Not the heat of a fire, or a chemical reaction, or anything that burns in the ordinary sense. The heat of time itself. In a way, the slow, steady decay of radioactive atoms. Voyager 1 carries 3 devices called radioisotope thermoelectric generators, RTGs, in the shorthand of the engineers who built them. Each one is loaded with pellets of plutonium-238, a material that releases heat as its atoms gradually break apart. That process cannot be switched off. It cannot be accelerated or slowed. It simply continues, at its own pace, governed by physics rather than by human intention. The heat those pellets produce is converted into electricity through something called the Seebeck effect, a quiet phenomenon in which a temperature difference across certain materials generates a small electrical current. There are no moving parts in this process. No turbines, no pistons, no pumps. Just heat on one side, cold on the other, and a steady trickle of electricity flowing between them. It is, in its way, one of the most elegant things humanity has ever built into a machine. When Voyager 1 left Earth in 1977, those 3 generators together produced about 470 watts of electrical power, enough to run a few household light bulbs. Not much, by any ordinary measure, but sufficient for a spacecraft designed with extraordinary care. By 2024, that output had fallen to roughly 240 watts. The decline is not a malfunction. It is simply the nature of radioactive decay. Plutonium-238 has a half-life of about 87 years, meaning that after 87 years, roughly half of its atoms will have broken apart and the heat output will have halved. Voyager 1 is not yet at that threshold, but it has been traveling for nearly 47 years, and the slow diminishment is real and measurable and irreversible. 240 watts. That is less than the power drawn by a modest desktop computer, and yet it must sustain a spacecraft, keep certain components from freezing in the deep cold of interstellar space, and transmit a signal across more than 23 billion kilometers. To make that possible, NASA has spent years making careful, sometimes painful decisions about what to turn off. Instruments that completed their primary work were powered down. Heaters that once kept components within safe temperature ranges were switched off, one by one, as engineers calculated which systems could survive the cold and which could not. Each decision was a kind of letting go, an acknowledgement that the mission, however extraordinary, is finite, and that the remaining power must be rationed with precision. What remains, as of the mid-2020s, is a small constellation of instruments still listening to the universe around them. The plasma wave subsystem continues to detect oscillations in the interstellar plasma, the faint electrical tremors that allowed scientists to measure the density of the medium Voyager now moves through. The magnetometer continues to sense the direction and strength of the magnetic field in the very local interstellar medium, building a record of a region no other instrument has ever sampled directly. The cosmic ray detectors continue to count the high-energy particles streaming in from distant supernovae and other violent events scattered across the galaxy. These instruments are not dramatic. They do not take photographs. They do not produce images that can be shared or easily explained. They produce numbers, streams of data encoding the quiet, invisible properties of a region of space that no human will ever visit in person. And those numbers are still coming, still traveling back across the dark. The signal Voyager 1 transmits is sent using a dish antenna about 3.7 meters across, roughly the width of a large dining table. The transmitter produces about 22 watts of radio power, less than a standard light bulb. That signal travels at the speed of light, roughly 300,000 kilometers every second, the fastest anything in the known universe can move. And still, it takes more than 22 hours to arrive, more than 22 hours for a signal moving at the speed of light to cross the distance between Voyager 1 and the antennas waiting for it on Earth. That number is not a metaphor or an approximation of vastness. It is a precise, measured fact, updated regularly as the spacecraft moves farther away, and it grows, slowly, with every passing day. When the signal finally arrives, after that 22-hour journey, it carries almost nothing in the way of energy. Roughly 20 femtowatts, 20 quadrillionths of a watt. A number so small it is nearly impossible to hold in the mind. If you gathered the signal energy arriving from Voyager 1 over an entire year, it would not be enough to power a digital watch for a single second. It would not be enough to light the smallest LED for a measurable moment. And yet, it is enough. Because the antennas waiting for it are enormous, and the electronics processing it are exquisitely sensitive, and the engineers who designed this system understood that the signal would be almost nothing by the time it arrived, and they built accordingly. NASA's Deep Space Network maintains the antennas that receive Voyager's transmissions, great white dishes, some of them 70 meters across, positioned on 3 continents, so that as Earth rotates, at least one antenna is always facing the right part of the sky. They are among the most sensitive radio receivers ever constructed, capable of detecting signals that carry less energy than a single snowflake landing on still water. And so the conversation continues. Slow and faint, and stretched across a distance that grows by roughly 1.5 million kilometers every day, but continuous. A thread of human contact reaching out to a machine that has traveled farther than anything we have ever made, into a region of space that was, until very recently, entirely unknown to us. There is something worth sitting with in that image. A 22-hour delay between question and answer. A signal arriving with the energy of almost nothing. A spacecraft running on the slow decay of atoms, its power halved from what it once was, its instruments reduced to a careful few. And still transmitting? Still measuring the plasma density of the interstellar medium, still counting cosmic rays from distant stellar deaths, still sending its quiet numbers home across the dark, 1 to 2 hour journey at a time. Somewhere in the direction of Ophiuchus, right now, as you lie here in the stillness, Voyager 1 is moving. And somewhere on Earth, a great white dish is listening, waiting for a whisper that left the spacecraft yesterday morning, that has been traveling through interstellar space, and then through the inner solar system, and then through the thin shell of Earth's atmosphere. And that will arrive, carrying almost nothing, and be received, and decoded, and added to a record that has been building for nearly half a century. The universe is very large, and the signals we send into it are very small. And somehow, for now, they are still finding their way home. Those great white dishes have names and addresses. The antennas that receive Voyager's signal belong to a network called the Deep Space Network. 3 clusters of enormous dishes, positioned on 3 continents, spaced roughly evenly around the Earth. One in the Mojave Desert of California, one outside Madrid in Spain, one near Canberra in Australia. The spacing is deliberate. As the Earth rotates, one station turns away from Voyager's position in the sky, and another rotates into view. So the watch is continuous, unbroken. Somewhere on Earth, at every hour of every day, at least one of those dishes is pointed toward the constellation Ophiuchus, listening. It is a quiet kind of vigil. The dishes themselves are large enough that standing beneath one feels something like standing beneath a building that has decided to look upward. The largest are 70 meters across. Their surface is shaped with great precision because the signal they are waiting for has so little energy that even small imperfections in the dish geometry would scatter it into noise. Everything about the receiving end of this conversation has been engineered around the fact that Voyager's voice, by the time it arrives, is almost inaudible. And yet the conversation has continued, more or less without interruption, for nearly half a century. More or less. In late 2023, it stopped. Not because Voyager had gone silent by choice, not because the distance had finally become too great, but because of something much smaller, and in its own way, much more unsettling. A single chip inside Voyager 1's flight data system had developed a fault, a piece of memory, corrupted. And the effect was that the spacecraft began sending back data that made no sense, garbled, unreadable. The numbers arriving on Earth after their 22-hour journey were not numbers that corresponded to anything real. For the engineers receiving them, it must have been a particular kind of silence. The signal was still there. The spacecraft was still transmitting, but what it was saying could not be understood. Several months passed. The team worked carefully through the problem from Earth, knowing that every command they sent would take over 22 hours to arrive, and that any response would take another 22 hours to return. A single exchange, one question, one answer, required nearly 2 full days. There was no room for hasty decisions, no room for trial and error in any rapid sense. Each step had to be thought through completely before it was sent, because the confirmation of whether it had worked would not come back until the following day. What they eventually determined was that a portion of the flight data system memory, roughly 3% of it, had become unusable. The data meant to pass through that section was being corrupted in transit. The solution they devised was, in its essence, elegant. Rather than trying to repair the damaged memory, they would route around it, divide the affected code into sections, and store those sections in other parts of the memory that were still intact. Redistribute the contents of a broken room into the rooms that remained. The commands to do this were sent across roughly 23 billion kilometers of space. 23 billion kilometers. It is a number that resists easy comprehension. The distance from Earth to the Sun is about 150 million kilometers. Voyager 1 is now more than 150 times that distance away. If the Sun were a single step from where you are lying now, Voyager would be more than 2 city blocks away, and the engineers were attempting, from that single step, to reach into a machine 2 city blocks distant and rearrange its memory. The round-trip time for the repair confirmation, sending the command and receiving word that it had worked, was approximately 45 hours. And it did work. In the spring of 2024, Voyager 1 began returning clean, coherent data again. The numbers made sense. The instruments were reading. The spacecraft, after months of speaking in a language no one could interpret, found its voice once more. There is something in that story worth resting with for a moment. Not the drama of it, but the patience, the willingness to work slowly, carefully, across an almost incomprehensible distance, on a machine that no human hand will ever touch again. The engineers who sent those repair commands could not see the result of their work for nearly 2 days after sending it. They could only wait and trust the physics and listen. And the dish in the Mojave, or Madrid, or Canberra, whichever one was pointed toward Ophiuchus that morning, received the answer. Voyager 1 is not alone in this. It has a twin. Voyager 2 was launched 16 days before Voyager 1, in August of 1977, on a different trajectory that would eventually carry it past Jupiter, Saturn, Uranus, and Neptune. It took a longer path through the solar system, and it crossed the Heliopause later. In November of 2018, Voyager 2 passed through the outermost boundary of the Heliosphere and entered interstellar space. They are the only two spacecraft ever to have done so. But they did not cross at the same place. Voyager 2 entered the interstellar medium at a different location and a different angle than Voyager 1 had 6 years earlier. And this turned out to matter enormously, because the Heliopause, as Voyager 1's data had already suggested, is not a uniform surface. It does not look the same from every direction. Its thickness varies. Its structure varies. The way the solar wind pressure balances against the interstellar medium pressure is not identical from one point on the boundary to another. Having two spacecraft cross that boundary at different places was, in effect, like having two travelers enter a vast and unmapped territory through different gates and then compare notes on what they found at the threshold. What they found was that the gates were not the same. The heliopause that Voyager 2 measured had different properties from the one Voyager 1 had measured. The thickness of the boundary region, the behavior of the plasma, the precise way the magnetic field shifted. These things varied between the two crossing points in ways that no single spacecraft could have revealed. The boundary of our solar system, it turns out, is not a simple line drawn evenly around a central point. It is a complex, living surface, shaped by the sun's activity, by the motion of the solar system through the galaxy, by the local structure of the interstellar medium pressing in from outside. 2 data points are still only 2 data points, and scientists are careful to say that much remains uncertain. But 2 is more than 1, and the picture that emerges from comparing them is richer and stranger and more textured than any single crossing could have provided. Both spacecraft are still out there now, both still transmitting, though with diminishing power, both still watched over by the same network of dishes, the same patient antennas turning slowly with the Earth. Voyager 2 is moving in a different direction from its twin, southward, out of the plane of the solar system, toward the constellation Telescopium, while Voyager 1 continues outward toward Ophiuchus. Its twin traces a separate line into the dark. 2 thin threads, extending outward from a single point of origin. Both carrying golden records. Both carrying the faint electrical signatures of a civilization that built them, launched them, and has been listening for them ever since. The Deep Space Network listens for both, every day, without pause. A dish in the desert, a dish on a Spanish plain, a dish in the Australian hills, each one waiting for a whisper that is already more than a day old by the time it arrives. And the whispers keep coming, quiet and faithful and very far away. What those 2 crossings revealed, when placed side by side, was something no single spacecraft could have shown. The heliopause is not the same everywhere. Where Voyager 1 passed through it, the boundary had one thickness, one texture, one set of measurements. Where Voyager 2 passed through it, 6 years later, and in a different direction, the numbers were different. Not slightly different, meaningfully different. The structure of the boundary varied from one location to another, in ways that the models had not fully anticipated. This is what 2 data points can do, that one cannot. They can show you that a thing is not uniform, that the edge of the sun's reach is not a smooth, even surface, like the skin of a bubble. It is more like a coastline, irregular, shifting, shaped differently depending on where you stand. And that changes how we think about what the heliosphere actually is. For a long time, it was described simply as a boundary, the place where the sun's influence ends and interstellar space begins. But the Voyager data, taken together, suggests something more layered than that, a region with its own internal complexity, its own variations in pressure and density and magnetic orientation, a frontier rather than a line. And that frontier matters. not just as an object of scientific curiosity, but as something that has shaped the conditions for life on this planet. The heliosphere is, among other things, a shield. Galactic cosmic rays, high-energy particles born in distant supernovae, accelerated across vast stretches of the galaxy, stream through interstellar space in all directions. The heliosphere deflects a significant fraction of them before they can reach the inner solar system. Not all of them, but enough that the flux arriving at Earth's surface is meaningfully lower than it would otherwise be. Without that shielding, the cosmic ray environment at Earth's surface would be higher. How much higher, and what the long-term biological consequences would be, remains an area of active study. The effects would likely be gradual rather than sudden. Subtle shifts in mutation rates, in the chemistry of the upper atmosphere, in the slow processes that shape living things over generations. The heliosphere has been doing this quietly for as long as the sun has been producing a solar wind, which is to say, for billions of years, long before there were eyes to observe it, or instruments to measure it, or minds to understand what it was doing. Voyager 1 was the first thing we sent to the edge of that shield, the first object built by human hands to pass through it and continue outward. And the people who made that possible have grown old alongside it. The mission launched in 1977. The scientists and engineers who designed it, who calculated its trajectories and built its instruments and sent it on its way, were young then or middle-aged. Some of them have spent their entire careers watching Voyager 1 move outward, year by year, boundary by boundary. Some of them retired before the spacecraft reached the Heliopause. Some of them did not live to see it cross into interstellar space in 2012. There is something very quiet in that fact. A machine outlasting the people who made it, continuing its work after the hands that shaped it have stilled. The mission has now outlasted the careers of most of the scientists who designed it, and some of those original team members are gone, their contributions woven into the data that still arrives every day from beyond the edge of the solar system. The work continues, carried forward by a new generation of scientists who were children or not yet born when Voyager 1 left the Earth. But the spacecraft itself is aging. At launch, its 3 radioisotope generators produced about 470 watts of electrical power. By the mid-2020s, that output had fallen to roughly 240 watts. The decay of plutonium-238 is slow and steady and cannot be stopped, but it cannot be reversed either. Every year, a little less heat, a little less electricity, a little less capacity to run the instruments that are still listening. NASA has been making careful decisions about what to keep on and what to turn off. Heaters have been shut down. Instruments have been powered down one by one to preserve what remains for the instruments that matter most: the plasma wave subsystem, the magnetometer, the cosmic ray detectors, each one still returning data from a place no other instrument has ever been. The expectation, as of the mid-2020s, is that Voyager 1 will remain operable, with at least one functioning instrument, until somewhere between 2025 and 2030. The exact timing depends on how carefully the power is managed, and on decisions that have not yet been made. But the window is narrow now. The long twilight of the mission is already underway. And then, at some point, the last instrument will go quiet. The last signal will travel its 22-hour journey across the dark and arrive at a dish antenna somewhere on Earth, and the engineers monitoring the data will note the silence, and Voyager 1 will become, from that moment, unreachable, not lost. Its position will be known, its trajectory calculable for thousands of years, but silent, no longer sending. And yet, it will not stop. It will continue moving outward at roughly 17 kilometers per second, as it has been doing for decades, carrying its golden record with its sounds and music and encoded images of a world it left behind nearly half a century ago, drifting through the very local interstellar medium, through the thin gas and dust of the local bubble, through the long dark between the stars. In roughly 300 years, it will approach the inner edge of the Oort cloud, that vast, spherical shell of icy bodies that surrounds the solar system at enormous distances. It will spend perhaps 30 and 000 years passing through it, and then it will emerge on the other side into the deeper interstellar space beyond. In about 40,000 years, it will pass within 1.6 light years of a star called Gliese 445 in the constellation Heliopause, not close enough to be captured by its gravity. Just a quiet passage in the night, a small metal object drifting past a distant sun. And it will keep going after that. There is no force out there to stop it. No friction, no drag, no boundary it cannot cross. It will drift outward through the galaxy for longer than the Earth has existed. For longer, perhaps, than the sun has left to burn. The golden record will go with it. The sounds of wind and rain and ocean waves, the music of many cultures, encoded in the grooves of a gold-plated copper disc, the greetings in dozens of languages, the brainwaves of a young woman thinking about love and hope and the stars. All of it sealed inside a spacecraft that no one will ever touch again, moving through a darkness that has no end. There is something in that which is very hard to hold in the mind all at once. A message sent without any certainty of a recipient, a journey with no destination, a record of a world, carried outward into a silence so vast and so deep that the word silence barely covers it. And yet it goes, quietly, without ceremony, in the direction of Ophiuchus. Every day, a little further. Every day, a little more alone. And still, somehow, carrying something of us with it into the long, unhurried dark. And still it goes. Out beyond the Heliopause, out beyond the last whisper of the sun's wind, into a region of space that has no name. Most people would recognize. Voyager 1 moves through the very local interstellar medium, that quiet stretch of galaxy immediately surrounding our solar system. And even here, even at this almost incomprehensible distance, it has not yet reached the true outer edge of what we might call the solar system's domain. Because far beyond Voyager 1's current position, far beyond where the sun's wind falls silent, there is thought to be another structure entirely: the Oort cloud. It is not a cloud in any familiar sense. There are no soft edges, no visible mass. It is a vast, spherical shell of icy bodies, remnants from the earliest days of the solar system's formation, orbiting the sun at distances so enormous that the sun itself would appear as little more than a bright star among other stars. The Oort cloud is thought to begin somewhere around 2 falls astronomical units from the sun, and to extend outward, perhaps, to 100,000 astronomical units or more, a shell of frozen silence, enclosing everything we have ever known. Voyager 1 has not reached it yet. At its current speed, roughly 17 kilometers every second, about 3.6 astronomical units every year, Voyager 1 will not reach the inner edge of the Oort cloud for roughly 300 years, 3 centuries from now. Long after every person alive today has gone, the spacecraft will begin to pass through that distant halo of ice and ancient debris, and it will take perhaps another 30,000 years to exit the other side. 30,000 years. That is longer than recorded human history, longer than the oldest cave paintings, longer than the first cities, the first written words, the first ships that crossed open water. All of that, everything we have built and remembered and lost, would fit inside the time it takes Voyager 1 to pass through the Oort cloud, and it will pass through in silence, as it does everything. No one watching, no signal strong enough to reach us from that distance, just the spacecraft and the dark and the slow, patient pull of the sun's gravity, still faintly present even there. There is something quietly humbling in that image. A machine we built in the 1970s, still moving, still carrying its record, passing through a structure we have never directly observed because the Oort cloud itself has never been seen. It is inferred from the paths of long-period comets that fall inward toward the sun every few thousand years. their orbits suggesting they were disturbed from some vast, distant reservoir. The Oort cloud is, in a sense, a theory confirmed by shadows, by the comets that arrive as its messengers, long after whatever nudged them has been forgotten. And Voyager will pass through it without knowing. Back here, on Earth, the data Voyager 1 has already sent continues to be studied. The measurements it made crossing the termination shock, the Helios-heath, the Heliopause, those readings are still being analyzed, still appearing in scientific papers, decades after the spacecraft first began transmitting them. The interstellar medium turned out to be more complex than the models predicted, the boundaries more layered, more variable, more alive with structure than anyone had fully anticipated. And so the work continues. Scientists who were not yet born when Voyager launched are now publishing research based on its data. The spacecraft keeps giving, even as its power slowly fades. Every day, Voyager 1 travels roughly 1.5 million kilometers further from the Sun. That number is almost too large to feel. 1.5 million kilometers in a single day, quietly, without ceremony, in the direction of the constellation Ophiuchus. It does not accelerate. It does not slow. It simply continues, as it has continued for 47 years, carried by the momentum of a launch that happened before most of the people reading about it were alive. There are engineers at NASA who have spent their entire careers in conversation with this spacecraft, sending commands, waiting 22 hours for the signal to arrive, waiting another 22 hours for the reply, a single exchange taking nearly 2 days, and still they listen, still they send. Because Voyager 1 is still there, still measuring, still returning what faint data it can from the edge of everything we can reach. The signal arrives at Earth with almost no power at all, a whisper across 23 billion kilometers. And yet the antennas find it. The Deep Space Network, those great dishes pointed at the sky on 3 continents, turning slowly to follow a point of nothing in the dark. They find the signal, and they hold it, and they bring it home. There is something in that which feels like devotion. Not the devotion of certainty. No one knows how much longer Voyager will speak. Its power continues to decline, instrument by instrument going quiet. But for now, it speaks, and we listen, across a distance that light itself takes more than 22 hours to cross. The story of Voyager 1 is, in one sense, a story about limits. The limit of the sun's wind, where it finally yields to the pressure of the galaxy. The limit of the Heliosphere, that vast protective bubble that has sheltered life on Earth for billions of years without our knowing it was there. The limit of our instruments, straining to hear a signal fainter than almost anything we have ever tried to detect. The limit of human lifetimes, measured against the timescales of the journey. But it is also a story about what lies beyond those limits. The interstellar medium, thin and ancient and threaded with the remnants of stars that died before the sun was born. The local bubble, that low-density cavity carved by supernovae long ago, through which our solar system is quietly drifting. The Oort cloud, waiting in the far distance like a memory the solar system has not yet revisited. And beyond that, the open galaxy, patient and indifferent and immeasurably large. Voyager 1 is out there in all of that, right now as you lie here. Moving at 17 kilometers per second through a darkness that has no floor and no ceiling, carrying a golden record that no one may ever find, sending a signal that takes nearly a day to reach us, crossing a distance that grows by 1.5 million kilometers before tomorrow's sun rises. And somehow, it is still ours, still connected to us by that thread of radio waves, still answering when we call, still doing the quiet work of measuring and reporting from a place no human eye will ever see. The solar system is larger than we feel it to be, lying here in the dark. The sun's reach extends far beyond the planets, far beyond the places we have named and mapped. And even at the edge of that reach, where the sun's wind finally stills and the interstellar medium takes over, there is structure, there is complexity, there is more to understand than we have yet understood. Voyager 1 taught us that A spacecraft designed for a 4-year mission, now in its 5th decade, still teaching, still moving, still carrying something of us outward and outward and outward into the long, unhurried dark. And yet the journey is not finished. Not even close. Voyager 1 has been traveling for over 47 years now, since that September morning in 1977 when it lifted away from the Florida coast on a column of fire and smoke. It was meant to last 4 years, to visit Jupiter, then Saturn, then go quiet. But it did not go quiet. It kept going. And in keeping going, it became something no one had quite planned for, a messenger from the very edge of the sun's domain, and then from beyond it. The boundary it crossed in August 2012 is called the Heliopause. It is the place where the sun's outward pressure and the pressure of interstellar space finally reach an equilibrium, where the solar wind, which has been blowing outward for billions of years, simply stops. Not with a wall, not with a sharp line you could draw on a map, but with a gradual, complex transition that Voyager's instruments measured piece by piece. The crossing was confirmed not by a single reading, but by several instruments agreeing at once. The plasma wave subsystem detected a change in the density of the surrounding medium. The magnetic field instruments recorded a shift in field orientation. The cosmic ray detectors, which had been watching galactic particles stream in from outside, recorded a sharp rise in their numbers. And simultaneously, the lower energy particles that had originated from the sun fell away. All of it together said the same thing. Voyager 1 was no longer inside the Heliosphere. It was somewhere else entirely. The interstellar medium that greeted it is not empty. It is thin, extraordinarily thin, but it is not nothing. Mostly hydrogen and helium, with faint traces of heavier elements scattered through it, like dust on a vast, dark floor. Its temperature, near the Heliopause, is estimated at somewhere between 30,000 and 50,000 Kelvin, which sounds warm, but temperature, in a place with so few particles, carries almost no practical meaning. There is almost nothing there to hold the heat, almost nothing to transfer it. So the interstellar medium near the Heliopause is, in a physical sense, both extraordinarily hot and profoundly, utterly cold. The plasma density Voyager measured just outside the Heliopause was roughly 40 times higher than what it had measured inside the heliosheath, a significant difference, a clear signature that it had crossed into a different kind of space. But what surprised scientists most was not the crossing itself. It was what the crossing revealed about the boundary. The Heliopause had been modeled, predicted, theorized about for decades before Voyager reached it, and many of those models imagined it as a relatively clean, stable transition, a defined edge where one regime ended and another began. What Voyager found was more layered than that, more variable. The data suggested the Heliopause may have multiple sub-boundaries, regions within regions, structure within structure, and the boundary itself is not fixed. It breathes, in a sense, expanding slightly when the sun is more active, contracting during quieter periods, shifting inward and outward with the rhythm of the solar cycle. There is even a region just outside the Heliopause, detected not by Voyager directly, but through ultraviolet observations, where interstellar hydrogen piles up against the boundary like water against a dam. A hydrogen wall. Quiet, invisible, enormous. Voyager 2 crossed the Heliopause in November 2018, 6 years after its twin. It crossed at a different location, a different angle. And when scientists compared the two datasets, they found that the Heliopause is not uniform. Its thickness and structure vary from one place to another. Two crossings, two different stories, both true at once. The heliosphere itself, that vast bubble the sun has been inflating for billions of years, is not a sphere. It is elongated, compressed on the side facing the direction the solar system moves through the galaxy, shaped by forces larger than the sun itself. And within that bubble, life on Earth has been quietly sheltered from a significant fraction of the galactic cosmic rays that fill interstellar space. High-energy particles born in distant supernovae, traveling for thousands of years before reaching our neighborhood. The heliosphere turns many of them aside. Without it, the cosmic ray flux reaching Earth's surface would be meaningfully higher. What the long-term consequences of that would be, over geological time, is still a matter of careful study. Voyager 1 is now moving through what scientists call the very local interstellar medium, the region of space immediately surrounding our solar system. The solar system itself is passing through a larger structure called the local bubble, a low-density cavity in the galaxy, carved out long ago by ancient supernova explosions. Their light is gone. Their sound, if sound could travel through space, is long since faded. But the shape they left behind remains, and we are moving through it. Voyager moves through it too, at roughly 17 kilometers per second, about 3.6 astronomical units every year, in the direction of the constellation Ophiuchus, which rises and sets in the night sky above you, without any visible sign of what is traveling toward it. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis, not close enough to be captured by it, just a quiet passage in the dark, a small human-made object drifting through the long spaces between suns. The power that keeps Voyager alive comes from 3 small generators, each one drawing on the slow decay of plutonium-238. No moving parts, no combustion. Just heat, steadily released by radioactive decay, converted into electricity through a process that requires nothing but time and physics. At launch, those generators produced about 470 watts. By 2024, roughly 240 watts remained. NASA has been methodically shutting down instruments and heaters over the years, preserving what power is left for as long as possible. As of the mid-2020s, Voyager 1 still carries functioning instruments, the plasma wave subsystem, the magnetometer, the cosmic ray detectors, still measuring, still sending. The signal those instruments produce travels back to Earth at the speed of light, roughly 300,000 kilometers per second, and it still takes over 22 hours to arrive. By the time it reaches the large dish antennas of the Deep Space Network, spread across 3 continents, it carries a power of roughly 20 femtowatts, 20 quadrillionths of a watt, a whisper so faint it requires some of the most sensitive receiving equipment ever built just to hear it. And yet, it is heard. Every day, engineers listen for it. Every day, it comes. The data it carries continues to be studied, published, debated. Scientists who were not yet born when Voyager launched are now writing papers based on its measurements. The mission has outlasted careers, outlasted some of the people who built it. It has become something that belongs not just to a generation, but to the long, slow accumulation of human understanding. Somewhere out there, in the dark between the stars, a small machine the size of a compact car is drifting through interstellar space, carrying a golden record pressed with the sounds of a living world, measuring the faint oscillations of plasma that no human will ever touch, growing farther from us by 1.5 million kilometers every day. And the signal it sends, that thin, 20 femtowatt whisper, is crossing 22 hours of empty space right now, as you lie here, traveling toward us, arriving. Still, there is something worth sitting with in that image. A machine built by human hands, launched in the year 1977, is right now moving through the space between stars. Not metaphorically, not approximately. It has crossed the boundary, the Heliopause, that outermost edge where the sun's breath finally gives way to the older, quieter medium of the galaxy, and it is on the other side. It crossed that boundary in August of 2012, at a distance of about 121 astronomical units from the Sun, 1 astronomical unit being the distance from the Earth to the Sun, roughly 150 million kilometers, so 121 of those laid end to end. That is where the solar wind finally ran out of strength. The crossing was not announced by a single instrument. It was confirmed slowly, carefully, through a combination of readings, plasma wave data, magnetic field measurements, particle counts, each one telling a piece of the same quiet story. The density of the surrounding plasma increased sharply. The flux of high-energy cosmic rays from the galaxy rose. The lower energy particles streaming outward from the sun fell away, and the magnetic field shifted, not as dramatically as some models had predicted, but measurably, unmistakably, from the sun's orientation to that of the interstellar medium. The boundary, it turned out, was not what anyone had quite expected. Scientists had imagined something relatively clean, a transition zone, turbulent perhaps, but broadly uniform. What Voyager found was more layered than that, more variable. The heliosheath, that thick region of compressed, heated solar wind plasma lying between the termination shock and the heliopause, was not smooth. The solar wind inside it no longer flowed outward in a single direction. It churned. It folded back on itself. It behaved in ways the models had not fully anticipated. And the heliopause itself may not be a single boundary at all. Voyager's data suggested the possibility of multiple layers, sub-boundaries, regions of transition rather than a single clean line. The edge of the sun's domain is less like a wall and more like a shoreline, shifting, layered, shaped by forces pressing in from both sides. Those forces include the sun's own activity cycle. During periods of high solar output, the heliosphere expands slightly, pushing the heliopause outward. During quieter periods, it contracts. The boundary breathes, in a sense, over the course of years, moving inward and outward with the sun's long rhythms. Voyager 2 crossed the heliopause in November of 2018 at a different location and a different angle than its twin. That second crossing gave scientists something rare: two data points on the same boundary, sampled from different directions. And what those 2 points revealed is that the heliopause is not uniform. Its thickness, its structure, its precise character vary from one place to another. The edge of the solar system is not the same in every direction. Both spacecraft are now traveling through what is called the very local interstellar medium, the region of space immediately surrounding our solar system. The material here is thin, mostly hydrogen and helium, with traces of heavier elements. Its temperature, near the heliopause, is estimated at somewhere between 30,000 and 50,000 Kelvin, a number that sounds warm, even hot. But temperature in a near vacuum is a strange thing. So few particles are present that almost no heat can be transferred. In any practical sense, it is cold beyond imagining. The solar system itself is moving through a larger structure, a region of the galaxy called the local bubble, a vast, low-density cavity carved out long ago by the shock waves of ancient supernova explosions. Stars that burned and died before our sun existed left behind this hollow in the interstellar gas. And our solar system drifts through it now, slowly, as it has for millions of years. Voyager 1 moves through this space at roughly 17 kilometers per second relative to the sun, about 3.6 astronomical units per year, in the direction of the constellation Ophiuchus in roughly 40,000 years. It will pass within about 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. Not close enough to be captured by it, just a quiet passage through the neighborhood of another sun. The nearest star system to our own, Proxima Centauri, is not in Voyager's path, and even if it were, at current speed, the journey would take roughly 73,000. These are numbers that do not resolve into anything the mind can hold. They are simply large, quietly, incomprehensibly large. The power keeping Voyager alive comes from 3 small generators, radioisotope thermoelectric generators, fueled by the slow decay of plutonium-238. They have no moving parts. They convert heat directly into electricity through a process that requires nothing to spin, nothing to combust. At launch, they produced about 470 watts. By the mid-2020s, that had declined to roughly 240 watts. And so instruments have been turned off, one by one, over the years, heaters shut down, systems placed into a kind of minimal wakefulness. What remains active as of the mid-2020s includes the plasma wave subsystem, the magnetometer, and the cosmic ray detectors. Still listening, still measuring, still sending. There was a moment in late 2023 when the signal went wrong. A faulty memory chip had corrupted part of the flight data system. For several months, the data coming back was unreadable. Engineers worked carefully, across a distance of 23 billion kilometers, to find a way around the damaged chip, to route the data through memory that still functioned. The round-trip time for a single command and its confirmation was approximately 45 hours. Send a message. Wait nearly 2 days. See if it worked. It worked. Contact was restored. The data began flowing again. Coherent, clean, continuous. That repair, conducted patiently, across a gulf of space that light itself takes over 22 hours to cross, is its own kind of quiet testament to something, to the long attention that humans have paid to this small machine, to the care that has kept it alive, instrument by instrument, year by year, decade by decade. Voyager 1 is expected to remain operable with at least one functioning instrument until somewhere around 2025 to 2030. The exact timing depends on how carefully the remaining power is managed, on which instruments are kept, and which are let go. And after that, after the last instrument falls silent and the last signal fades below the threshold of detection, Voyager 1 will continue. It will not stop. It will drift outward through the galaxy, carrying its golden record for as long as the galaxy exists. The record pressed with the sounds of wind and rain and human voices and music, sealed in gold, moving through the dark between the stars. Far ahead of it, though still centuries away, lies the inner edge of the Oort cloud, a vast, spherical shell of icy bodies thought to surround the solar system at enormous distances. Voyager will not reach that inner edge for roughly 300 years and will not emerge from the other side for perhaps 30,000 more. The solar system is larger than it appears. Its edges are not where the planets end. They extend outward, slowly, into the cold. And somewhere in that cold, right now, a small machine is drifting, 17 kilometers per second, in the direction of Ophiuchus, in the dark, carrying everything we thought to send. And the signal it last sent is still traveling, still crossing the distance, still arriving.